why are we doing these ledgers and blockchains and things? Why don't we just have a central server? Well, it's all about being able to create trust. We're being able to take weak forms of trust and turn it into stronger forms of trust, and we wouldn't have that with a central server. That's the whole point that we're here for. So the security of our systems, the fairness of our systems, all these weird things like Byzantine fault tolerance are actually very important. There we go, we have slides. These are actually very important things because the whole point of what we're doing is to be able to create trust. If we didn't care about that, we would just use a central server. We wouldn't even bother with these ledgers. So I want to talk just a little bit about trust in general, or the different types of things that we do to generate trust. Trust, of course, comes in many different flavors. Security comes in many different flavors. Fairness comes in many different flavors. I just want to talk briefly about some of these flavors. What do we have at the very bottom foundational level of all of our ledgers and blockchains and things? What do we look at for security and fairness? Especially fairness, because we don't talk about that very much, and it's really interesting. So we have Hashgraph, which is a system that does all these things, and it's an example I'll talk about at the very end. But I think what's really interesting is to talk about these things themselves. Security. The standard has been Byzantine fault tolerance for a long time. It comes in different flavors itself. The gold standard is asynchronous BFT. We'll talk about what that is. Fairness is a very generic term. Fairness of timestamps is an interesting concept. And then that can give you fairness of ordering, which is an interesting concept, and fairness of access. And these are critical things. And so let's just talk briefly about what these things are and why they're kind of hard to achieve, but how we can go about doing so. And then at the very end, I'll just really briefly go through how Hashgraph does these things. But the most interesting thing is just to talk about these properties themselves. So what is asynchronous BFT? Very mathematical term, 30-year-old terminology, and so on. Byzantine fault tolerance means we as a community of computers are going to reach agreement on these transactions that people are creating. We're going to reach an agreement on what they were and in what order they were. This is the bottom level of the stack. Then you can do things like, say, make sure that they're valid and make sure that they're immutable, and all that stuff can be built on top of it. But at the very base, at the foundation, we have to come to an agreement on the ordering of them. That's how you can stop double spend and everything else you're worried about. Now, to be Byzantine, you have to come to a moment when you know the order of a given transaction. You can't just have confirmations that keep making you a little bit more sure. Byzantine fault tolerance, this standard says there will be a moment when you know for sure exactly where in history this transaction goes and exactly what the timestamp is on this transaction. That is Byzantine fault tolerance. And you have to never be wrong. It has to be mathematically impossible for an attacker to get you to come to one conclusion and me to come to a different conclusion, even briefly, even just for a few seconds. So this is what Byzantine fault tolerance is. It's actually a pretty high standard, and it has been the standard for decades for distributed computing and fault-tolerant computing and distributed databases, ACID databases, all of these things. Because you have to know you reach consensus, you have to never be wrong, and you have to be guaranteed that you will reach consensus. Nobody can stop it. But even that comes in different flavors by what you have to assume to achieve that. So what you might say is, well, at least as long as the internet is working well, then I can guarantee this. As long as nobody ever shuts down a firewall over a part of the internet, I'll still achieve this. And as long as there's no botnets doing DDoS attacks on us, I'll achieve it. You might say that. As long as I have a good internet, I can achieve BFT. Or you could do something stronger. And you could say, no, even in a bad internet, I'll still achieve BFT. And so it all comes down to the assumptions we're making. We're going to have to assume that less than a third of us are attacking, less than a third of our nodes, or less than a third of our stake if we're doing proof of stake, or less than a third of our hashing power if we're doing proof of work. We have to assume that less than a third of our influence is attacking. Why? Well, there's theorems that say no system can survive a third. If you have malicious firewalls and a third of us are attacking, no system can survive it. No system could be asynchronous BFT. So we have to assume that. We have to assume that the attacker controls the internet. That's the whole point of being asynchronous here. The attacker can slow down messages by as much as they want. They can delete some messages and not others, as much as they want. They do have to eventually let a message through. We have to assume that if I keep sending you messages, eventually one will get it through. And then if I do it again and keep sending you messages, another one will get through, and so on. But that's the only assumptions we're making. Other than that, the attacker can control the internet. And if we're not making any further assumptions, then we are asynchronous BFT, which means we can survive DDoS attacks and firewalls and other things, as long as, if I keep sending you messages, eventually one gets through, and less than a third of us are attacking. So this is the standard for security. This is, in some ways, there's theorems that say you could never have a higher standard, and this has been the gold standard for decades of what we might want to have in a distributed consensus system. And so it'd be nice to have, our ledgers having this. So that's asynchronous BFT. One interesting way of making fast consensus systems is to have a leader involved. So there's Paxos and Raft with their leader-based systems. Basically, the easiest way to put transactions in order is to have a dictator that puts them in order for you. Well, just have a king who decides what the order is, and that's our order. And there's even systems that don't look like leader-based, but they are. Maybe we take turns being king for 2 seconds each, and we go around in a circle. That's also leader-based. Or we have a coordinator of some kind. So there's lots of ways that there are leader-based systems, sometimes even hidden that's actually leader-based. And leader-based is fantastically nice and simple. It's a little bit complicated when the leader crashes. You have to get a new leader. That's the complicated part of it. But you can get Byzantine fault tolerance with the leader-based system. Maybe not asynchronous, but you can get Byzantine fault tolerance. So why can't you get asynchronous? Because of things like DDoS attacks. Here we go. First of all, imagine that in this network, these 4 computers are trying to come to an agreement on the ordering of transactions, and the way we do it is Alice is going to be our leader. Everybody sends Alice their transactions. She puts them in order in whatever order she feels like, and maybe she's malicious and leaves them out, but whatever. She picks the order and then tells us all what the order is, and then maybe we all sign off on it, and now it's the official order. Bob, however, is malicious. Maybe his computer was infected with a worm or a virus, and so he is going to attack us, and so he also has a botnet. He has compromised lots of little computers on the internet, printers and other things. We've had DDoS attacks, the Dyn attack last fall, and so on. So Bob has this botnet, which are lots of little computers on the internet, and they all flood Alice with packets, and they shut her down. Now, of course, if his botnet is big enough, he could shut down all our computers, and we're out of luck. You can't have the network running. But this is bad. Here, he only has a big enough botnet to shut down just one computer, but by shutting down Alice, he's shut down our whole network for as long as the attack is going. That's disastrous. Oh, but wait. These leader-based systems have systems for choosing the next leader. Maybe we all notice that Alice is quiet for several seconds, and so we all pick a new leader. Maybe we all pick Carol. Or maybe we have a new leader every 2 seconds. So, Alice is shut down for 2 seconds, but 2 seconds later we go to Carol. And so what we would like is we just switch to Carol being our leader, and all those bots are attacking Alice, and that's unfortunate for Alice. I feel sorry for her, but the whole network keeps running. This is what we would like. Except Bob was compromised, remember? And Bob knows who the leader is, because a leader-based system requires us to know who the leader is. And so you know what Bob tells his botnet? Hey, everybody, Carol's the new leader. Attack Carol. And so we can play follow the leader, and Bob can keep the entire network shut down for as long as this attack is going by only shutting down one computer at a time. That is what it means to not be asynchronous. Asynchronous means we could handle one computer at a time being shut down. We could handle almost a third of our computers being shut down. That's what asynchronous means. There are lots of BFT systems out there that are not asynchronous, and the first question you always have to ask is, hey, how do you handle DDoS attacks? So this is why this is the gold standard in that community, this community too, I hope, of asynchronous Byzantine, because it's helpful. But then we also have to worry about fairness. And this is really interesting because this is something people haven't talked about as much. We want, as a community, to put timestamps on our transactions. If we have a stock market, and you put in a transaction bidding on a stock, and I put in a transaction bidding on a stock, we need to all agree whose transaction counts as being first, because maybe there's only one share left. And if you're first, you're going to get it. And if I'm first, I'm going to get it. Or if we're playing a game, and it's a first-person shooter game, you shoot me, and I dodge. Well, if you shot before I dodged, you get a point. But if I dodged first, then you don't get a point. We care which one is first. And so what we need to do as a community, we need to put a timestamp on these things, and that'll tell us who is first. But it needs to be fair. So what does that mean? What does it mean to have fair timestamps? Well, what we mean is that the timestamp should be the truth, and maybe just a malicious person can only adjust it slightly from the truth, but not very far. If that person makes up 1% of the population, they can only have 1% on the influence of drifting us away from the truth. So we want our timestamps to be the true timestamp, not just a timestamp that a leader made up, not just a timestamp that the person who creates the transaction makes up. We want to truly know, when did your transaction reach the community? So let me show you what I mean by this. How do we even get information out in a non-leader-based system? Well, gossip is the simplest way to do this. Lots of systems use gossip. In computer science, this is pretty much the fastest way we know to get information out, the most resilient. DDoS attacks can't do much damage on this. This is a great way to get information out, which is why everybody uses it. What does it mean? Alice has a message. Maybe she's created a transaction. And so what Alice does is she has her message there, the red envelope, and she picks a person at random and gives it to them. She picks Dave and gives it to him. And now, instead of one person knowing the secret, 2 people know it. And then what do each of them do? Each of them picks a random person and gives it to them. And now 4 people know it. And then each of them picks a random person and gives it to them. And now 8 people know it, and then 16, and then 32, and then 64, and it explodes outwards. In just 10 steps, we've reached 1,000 people. In just 20 steps, we've reached 1,000,000 people. In just 30 steps, we've reached 1,000,000,000 people. You can reach the entire planet in just 33 steps. So this is nice. The message goes out exponentially fast. Great. This is a great way to spread our transaction. We don't have consensus yet on timestamps, but it's a good way to get our messages out. And what if other people have transactions they want to send out, other messages? Say Bob wants to send out that green message that he just created, and Carol wants to send out that blue message that she just created. What do we do? Well, if we're doing old database systems with 2-phase commits and locks, they have to take turns. If we're doing a leader-based system, they have to give their messages to the leader, and the leader then calls everybody up one by one and gives them the messages in the approved order. But we don't want to do that. We want to be resilient and no leader, and everybody is the same and as fast as possible. So what do? Well, the simplest thing is we just talk. Each of them calls somebody at the same time and gives it to them at random. And now 2 people know green and 2 people know blue. And then we do it again. And now 4 people know green and 4 people know blue. And then 8 people know green and 8 people know blue. And before you know it, the whole world knows it. And we didn't do any coordination. We didn't take any turns. We just talk. When you want to talk, you talk. This is the fastest, most resilient thing I can possibly even imagine. And so what happens then is they all get it. Now, they all got them in different orders. So we want to put timestamps on these things. We want the timestamp to be the truth. What is the true timestamp? The true timestamp is the time that the message reached the community. So what's the true timestamp on that green one? I don't know. What was the true time that the green one reached the community? What does that even mean? The community's not a computer. It's a bunch of computers. It didn't reach the community at an instant. It reached it at a whole bunch of times. So just philosophically, what do we mean as the time at which the green one reached the community? Yeah, so you said average. You could also talk about median. You could talk about all sorts of things. And you know what? Median is equivalent to saying it's when we reach most of the people. We'll just say, at what moment in history did the green one have reached most of the people? When can we say, okay, the green one's reached most of the people? Yeah. So it's the median, which is like an average, except it's better for rejecting outliers, even better. So here's what we're going to say the true timestamp should be is when I reached most of the people. And so I could say, well, what time did the green one reach most of the people? What was the instant when just over half of us finally had the green one? And what's the instant when just over half of us had the blue one? By the way, with this exponential thing, one more sync, one more step, and everybody knows it. Once you reach half the world, it just takes one more step and the whole world knows it. Right? Once you know half a billion people have it, you just talk to one more person and now 1 billion people have it. And so we'll say that the true timestamp really ought to be when you've reached half the community, the median of all those timestamps. So what should the consensus be? Okay, well, maybe the consensus is just I ask each person, when did you receive it? And then I take those times, put them in a sorted order, and we take the middle one from that list. Okay, so that's kind of simple. Let's see what this looks like. I'm going to show you that same picture I just showed you. Here's the history. Alice, remember, talked to Dave first. I'm going to draw a little circle for Dave. That's the event where he received something from Alice. And then each of them talked to someone else. Alice there talked to Gina, and Dave talked to Bob, and then it went on, and then we had 4 people, and then 8 people. This is just another way of illustrating the picture I just showed you before, except instead of needing a sequence of pictures, it's all in one place. This is a nice little graph of how we talked. The red circles are when each person first heard this message. So if all of these circles had the timestamps on them of when the person received the message, this would be a picture that would instantly tell us the consensus timestamp for the red message. And how about the green one? Yeah, same thing. The picture can tell us the consensus timestamp for the green one. And how about the blue one? Wow, the picture's getting complicated now, but the same thing. Oh, and the green and the blue are both bidding in the stock market. Who was first? Well, we'll just take the consensus timestamp for the green and the consensus timestamp for the blue and see which one came first. We'll just put them in order by timestamp. Now, is this fair? What if someone lies about when they received it? What if Hank on the far right puts false timestamps on the blue and the green and the red circle? Well, okay. We have this big list of times. If he puts a time 1,000,000 years in the future or 1,000,000 years in the past, then he'll just be at one end of the list. But the vast majority of the times in the middle of the list, he doesn't really affect those. He just has a slight influence on which of those we pick. In fact, in this exponential explosion thing, most people will get it about at the same time. So the middle of our list is going to be a whole bunch of times that are all very close to each other, and a few attackers just slightly adjust which of those we choose. In fact, if the majority of us are honest, then the middle one on the list is guaranteed to be an honest time coming from an honest person or be between 2 honest times. We have fairness of timestamps. So that is what we can mean by fairness of timestamps. And that's how we could achieve it if only we had that picture. Oh, guess what? Turns out you can get that picture almost for free. The Hashgraph algorithm just says we talk to each other and we add just a tiny bit of information, 2 hashes, and you magically get this entire history in your memory. Every computer has the same picture here in their memory, and everybody can figure out the consensus all by themselves without talking to anyone. And that's it. Do I have time for some questions?
We have time for just a few questions. And,
okay.
If you could raise your hand and wait till I bring you the microphone to ask the question, it will help with the audio. And
okay.
While he's answering the question, if you want to raise your hand for the next question.
Yes.
Hey, can you talk about what happens when nodes or majority of nodes go down?
Yes, you freeze. There's a theorem that says, what we'd like to do is keep going and also be secure. Totally impossible. The problem is if I could keep running with less than half of us up, then you could partition my network and each half would keep running independently. We'd have 2 different ledgers that contradict each other. So you have to freeze. So there's a theorem that says nobody can survive that. No one can survive even a third going down if you're worried about malicious firewalls and you want to be correct. And so you either give wrong answers or you freeze until the partition's healed. The freezing solution is much better. Exactly, right. So on the CAP theorem, that's exactly what you want. Yeah, right, exactly.
What
you
was
want
the point?
So his question was, you're giving up the availability in terms of in favor of consistency, which was a reference to CAP theorem, consistency, availability, partition, resilience. And yes, we want a CP system. Turns out you can also build an AP system on this, but I'm not very interested in that. I'm much more interested in a CP system. Yes.
We got it
yes.
Here.
Hi, thank you, Mr. Baird. Yes, can you hear me?
I can hear you.
Yeah. So in the Hashgraph world, what is the size of Hank F? So that how many Hanks would it take to bring down the system? Like,
1/3.
It's the same.
It is the same. Sorry. Yes. 1/3 brings down the system. So there's a theorem that says nobody could be better than that, and we are not worse than that. We've achieved what mathematics allows.
Okay,
yes.
Great. Thank you.
I'm trying to fully understand the algorithm and where we pick the median. And if the number of people who knows is doubling at each point in time, and we're taking a median, which is right in the middle, like does that median occurs right at the point of the last doubling for graphs, well, I guess that are at or close to a power of 2. So and I don't really understand the time scale, but it worries me a little bit that I don't understand whether the median would be on like the second to last or the last or in between. And to me, that makes a difference as to whether or not a malicious actor could actually adjust their data to affect the timestamp. Is my question clear?
So possibly. So let me rephrase this. So everyone gets to affect the timestamp. If the attacker is 1% of the population, they get to affect 1% of the weight on the timestamp. But because we're taking a median, what we're doing is we're having everybody in the community put their time in this list. We're going to sort all the times. What can an attacker do? They could put their time a million years in the future or in the past, but all that does, when you take one number on a list that's sorted and you move it at the top or the bottom, now the middle just slid to one right next to itself. So they had very little influence. If we did an average, they could have a huge influence. You average in the number 1,000,000 and the whole number gets really big. But if we're doing a median, they have only a tiny influence. And so attackers absolutely can influence, just like anybody can, but only a tiny amount, if they're in the minority. If they were in the majority, then they can destroy everything.
Thank you, Leemon.